Hi there, Anita. How are you doing? Can you hear me okay? Sorry, my camera's been playing up. I don't know what's going on, but I don't know if you can hear me okay. Can you hear me fine? Hello? Hello, Anita. Can you hear me? For some reason, can you hear me? I'm just going to go in the chat and type to you. Can you hear me? Or is there an issue with the sound? Can you hear me through your speaker?
Yeah, I can hear it now.
Oh, fantastic. Excellent. Excellent. Super stuff. Super duper. How's your week at school been? And any updates? Have you had any assessments and such? Any updates?
It was all right. We didn't have any assessments.
Okay. And do you have an idea when your end of year tests will begin?
Oh, we've done ours.
Oh, you've done them already?
Yeah.
Awesome. Oh, that is awesome. So that means there's no pressure and you're still carried on learning waves in class?
Yeah, we are.
Okay. And what are you covering so at the moment in waves?
We did sound waves.
Okay, good. So most of the stuff that you covered, we had already spoken about. Was it quite familiar then?
Yeah.
Good. Okay. Awesome. So just to start off with, I thought we're gonna go through some questions just to see how well your understanding is coming along within the topic. So when you're ready, we're gonna start off with number 24, as it were. So have a go at that.
Sure.
Cool.
Yeah, is it B?
So you've chosen B for that one. Yeah, you're absolutely right. R will be moving down and S will be moving up. Good. Very good start. Excellent. Okay, we move on to number 25.
Is it B?
Is it B?
Yeah.
Not quite. So whenever you're looking at this, you should always look at what is on the x-axis. So there
A.
A. Okay. If this was distance, then yes, it would have been B, but it's time, so it's A. Good.
Right.
Number 26.
Mm. Um, is it wait, sorry.
No worries.
Mm. Yeah. Are there any more options?
No, just A to D.
Oh. Mm. Is it C?
Not quite. So tell me what you did then for this one. What was your approach for this one?
Oh, I use the equation.
Use the equation. Good. And which equation did you use?
1/5.
Lambda over.
Yeah, lambda over Yeah, I used the V equals lambda F1.
V equals F times lambda.
Yeah.
Good. That's the formula we need to think of. Good. So and we're trying to find out F, aren't we?
Yeah.
What did you work out as lambda, your wavelength?
Wavelength is 0.15.
0.15? Not quite. Because can you see that here we go. We've got a crest, a crest, a crest, and each of these distances here is a wavelength.
Do I divide by 3?
So you've got to divide this by 3. You're absolutely right. Yeah. So the wavelength therefore is 15 divided by 3.
Yeah, 0.05.
Very good. So 0.05. Now, do we know? So it's F times 0.05. Can we work out the speed?
S equals VT.
Yeah. Okay. And what does it give you as the speed then?
Is it 0.05 times 5?
Not quite in this case. So we've been told that it travels one crest, which is this wave front. It travels a distance of 15 centimeters in 5 seconds. So what is the speed of the wave? Distance divided by time. It travels 15
divided by 3 centimeters per second.
You're absolutely right. Yeah. So it would be 15 divided by 5, which would give us 3 centimeters per second, or 0.03 meters per second, if you change that to meters.
Yeah.
And the reason why I'm doing this is because my wavelength is in meters. So that's why I've had to use meters per second. So you get 0.03 as your speed. So what is F? So F is equal to 0.03 divided by 0.05, which is 3/5, which is 0.6 hertz.
All right.
Did you follow that okay?
Yeah.
Good. Okay. Next one. Okay, 28.
Is it A?
It is A indeed, order. So we'd be expecting to travel much quicker in a solid than in air. Good. Okay, we'll move away from that. We're not going to do energy questions. We're not going to do those ones. You've already done your exam, so we're not going to do general revision. We're going to still focus on the waves. Okay, number 26, as it were.
Is it up?
Is it up?
Yeah.
How did you work it out to say it's up? How did you work that one out? That one?
I guessed it.
Okay, there's a way of doing it without guessing it. So this is the wave in this moment in time, and it is moving in this direction. Yeah. So after a few seconds later, where will the wave be? That's the question we need to ask ourselves. It's going to be somewhere here.
All right.
So it's moving in that direction.
Yes, it's going right.
No, but remember, this is a transverse wave. And in a transverse wave, how do the particles move?
Up and down.
Now, we never use the word up and down. I know exactly what you mean, but the particles oscillate or vibrate perpendicular
to
the direction the wave travels. So where is this wave traveling? It's going this way. So it's a transverse wave. So how will the particles be moving? They'll be doing this. So where will this particle be next?
Down.
Down here at that position. So it can't move to the left. It can only move. It's only going to be moving up and down like that. Likewise, any particle here will just be moving up and down as the wave passes through. So we can see that particle A in this instance is moving down. So the answer is B. Okay, and that is how, because you know you had a similar question last time. The first question you did, I thought you knew how to do it. I should have asked you and I said, how did you get that one? But I'm glad that we've done this because then now I've explained to you how to think about it. Okay, cool. I'm moving on. Number 27. Oops, too far. 27.
I don't know.
Not sure how to do this one?
Not
okay,
sure.
So that's okay. So let's look at it again from the key thing to whenever you I don't know what they tell you in your school, but one thing I always tell my students is I try and tell them to remember this. Wow. Especially with physics. Do you know what this stands for?
No.
So the F is for, when you look at a question, first thing you want to think is, okay, what formulas might I need? That's the first question you ask yourself. Once you've done that and you're happy with what formula to use, ensure that you then show you're working. Once you've shown you're working, make sure that it's clear what your final answer is, and also that you ask yourself not to forget the units. Sometimes I also put an S, and this stands for significant figures. So when you write your answer, check that it is to the right number of significant figures. So sometimes the question will tell you, at times you have to make the judgment. So don't write everything on your calculator display. That would generally lose your marks, okay? So that's what this stands for. So let's try and use it. So what formulas do you think might be useful in this particular question?
S equals V2.
Yeah. Or even V equals F times lambda. Because this is the equation that relates wave speed to frequency and the wavelength.
Yeah.
How might we use this formula then?
Yeah.
Can you tell me what the wavelength is? Can you work that out?
Is a wavelength 10?
Okay, have another go. It's not quite 10.
0.1.
Not quite. So if I have a wave, what do we mean by a wavelength? So what is the wavelength of this wave? What do we
20.
measure? Good. From there to there is one wavelength. From there to there is half a wavelength.
Yeah.
Good. So the wavelength is, and it wants the speed in centimeters per second. So we're going to have to leave our wavelength in centimeters. So wavelength is 20. Now, what is the frequency?
Unknown.
How can we work that out?
1 over 1.5.
Correct. So I've got 1 over 1.5. Now 1.5 is the same as 3 over 2. So 1 divided by that, so it's 2 over 3 is the frequency. 40 divided by 3, roughly this will be 13.3, recurring, doing something like that. And our answer would be in centimeters per second. So the answer here is A. You happy with that?
Yeah.
Good. Number 29.
Yeah, so is the velocity 0.5 or 20?
So a bat flying towards a wall at 0.5 meters per second emits R. So that's the speed of the bat. That's the speed of the bat, not the speed of the sound wave.
All right. Is it 0.0005?
That's not on the answer options here.
Oh. Is it D?
D?
Yeah.
Not quite D on this one. So what did you do for this one? Do you want to talk me through how you approached it?
This is 40,078.5 times 10 to the power minus 3.
Oh, so you took 40,000 and then you multiplied it to 0.5.
No, to 8.5 times 10 to the power of minus 3.
Okay, and why did you do that? Just if you can explain why you went down that route.
I don't know.
Not sure. Okay. So key thing anyway here, you're probably realizing that there's a bit of a theme here with V equals F lambda, but because there's an echo that's involved, sound has to go to the vertical and come back, correct?
Yeah.
You happy with that?
Yeah.
Good. Now, what do we know? We know that the wavelength of the sound is given. We know that the frequency is given. So that is what we used here. which is this 8.5 times 10 to the minus 3 times, well, this is kilohertz. So we need to do something with this kilo and we change it to 40,000. Is that what you did, yeah?
Yeah, that's what I did.
Excellent. 40,000. So this is 40 times 10 to the 3. So 10 to the 3, that's 10 to the 0, 1. So then it's 40 times 8, 320, 320, 340. So you found the speed as 340 meters per second?
Yeah.
Good. And then how did you use this 340 meters per second? So then he said if it traveled, so it would have taken it, how long would have it taken it to travel one way if it took 20 milliseconds to go and come back?
Yeah.
So it took 10 milliseconds here, isn't it?
Yeah.
On just that trip, and then 10 milliseconds on the way back.
Yeah.
So if I want to work
3.4
out the
meters.
distance is VT, velocity times time. Yeah?
Yep, it's a 3 times 3.4.
Yeah, so which one did you say? A?
Yeah.
Correct, because 10 milliseconds is 10 times 10 to the minus 3 seconds. And that's what we're going to use. Then we're going to multiply these two using this formula here. You're right, 340 times 10 to the minus 3, which gives us 3.4 meters. And so our answer is A.
Yeah.
So far, so good with that one?
Yeah.
Excellent. Okay. We're going to do a slightly longer structured question, which involves some calculations. So a wave front. What is a wave front? Any ideas? A wave. Not sure about this one. Okay.
Sure.
So remember when we say you've got ripples and you're looking at ripples from the top, what you see is these kind of rings, isn't it? As the wave spreads out. Each of these ripples here, that line that you see, that imaginary line, I'm not going to say it's imaginary. Those lines that you see, those we call wave fronts. So a wave front is simply an imaginary line joining all adjacent points that are in phase. And what we mean by in phase, it simply means that they're doing the same thing. So all these here will be at the top of a crest. So if you had to look at this, it would look something like this.
Yeah.
Yeah. And of course, it would be a 3D pattern. So this would carry on. Okay. All right. The wave takes 3 seconds to travel from A to B. Determine the frequency of the wave.
Is it 1.5?
So you get 1.5 for that one?
Yeah.
Not quite.
Is it 1/3?
So you started off with the formula?
Oh.
Good. And so you rearrange this. Yeah?
Yeah.
So what do we know? How did you work out? So what is it says approaching a beach at a speed of 2 meters per second. So you know this is 2 meters per second. And what's the wavelength?
6.
Is it 6? Let's see, are we missing some information here? Shows a wave approaching a beach on the depth of the seabed. Can you actually do this?
Pardon?
I'm just trying to check the question again.
Oh.
8. The wave takes 3 seconds to go from A to B. Okay. Ooh, they're being very crafty. They're being very, very crafty.
Mm-hmm.
Wow, what a question. Okay, let's look at it then. They're being very crafty. So what is the wavelength? How are we going to find this wavelength? We know what this V is. How on earth are we going to work out that lambda? We know the wavelength is the distance from here to there.
Mm-hmm.
That there is the wavelength. So can you think of any clever tricks we could use to work that out?
Not really.
Not really? Okay. They're being very, very, very crafty. All right, let's think about this. So if the wave is traveling at 2 meters per second,
Yeah.
and how long does it take it to go from A to B? 3 seconds.
3 seconds, so 6 meters.
Very good. So this distance here is 6 meters.
Yeah, so 2 meters per wavelength. No, 3 meters.
Ooh, is it? How many waves do we have here? We have to be very careful.
Oh.
So we have how many waves? We have 1 wave. Oops. 1. That's 1 wave.
1.2,
2.
1.25, 2.25.
So we've got 2.5. Yeah. So 2.5 waves fit in 6 meters. Therefore, how many meters will 1 wave take? 2.5 waves fit in 6
6 divided 2.5.
6 divided by 2.5. What is that? You've got a calculator there?
Yeah. 2.4.
2.4. So that's the wavelength. Crafty little question. So now what are we going to do now? Now we found lambda. So we know the speed. 2 divided by 2.4.
Yeah.
What a question.
4.83.
What a question. And what do I need to put at the end of this?
Hertz.
Correct. Units. I would not say this is 2 marks. I would make this, I would say this is about 4 marks. Because you need to evaluate that. Then you need to do this. Then you need to do that. Then you need to find answer. This can't be 2 marks. This must be 4. It's not possible for 2 marks. Okay, good. Next one, part B.
Is it 3 times 10 to the power of 8?
No, that's the speed of light.
Oh, that's speed of light.
Yeah.
So do I half the 50 milliseconds and 80 milliseconds?
Yeah, so which formula we're going to be thinking again? I'm always trying to go back to, wow.
S equals VT.
Yeah. Good.
This is 17. So is S17?
Or is S17?
Yeah.
Yes.
Yeah, so do we halve the time and add them together?
So you have to halve the time. You're absolutely spot on.
Do we add them together?
Or do you add them together? No,
Yeah.
you wouldn't. So let's just visualize the problem a little bit. So the hole is 17 meters. When the student bangs a drum, 2 echoes are heard. So where's the student? Sits in the middle. So this is the student here. Okay. 2 echoes are heard, 50 milliseconds and 80 milliseconds respectively. So when they bang that drum, sound is going to be sent out in that direction. And sound will also be sent out in this direction, parallel to that face. So the sound has to, what does it have to do? It's got to go and come back.
Yeah.
And the time it takes to do this, how long does it take to go from there to there?
50.
50, correct. And it's also going to have to do the same this side.
80.
Correct. So if you want to work out the speed of sound, which values are you going to use?
Either one of them.
You can't use either one of them.
Or both of them.
So think about, why can't we use this one?
Because it's too long.
Not quite. Because we don't know what this distance is.
Oh.
Because the sound is traveling in this direction as the direction of that length.
Oh. And 680 meters per second.
Not quite.
Oh. Or is it not 17 divided by 0.025?
Okay, so just ask yourself, why did you say 17 divided by half of this time?
25.
Yeah, so half is 25 milliseconds. But just take your time now and think about the problem. So it takes 25 milliseconds to go from there to there. Yeah?
Yeah.
And what distance is it from there to there?
17.
Not quite. Not from here, not from the center to there.
Or it's 17 divided by 2.
Correct.
8.5. 340.
Correct. Okay, good.
Okay. Would it be 27.2?
So you get 27.2.
2.
27.2, you're spot on. Absolutely spot on. Good. And we'd have to put the units as well.
And meters.
Correct. Very good. Okay. Right. Awesome. So what we're going to do now very quickly is we are going to dive a little bit at the deep end, but it's good exposure to go to the deep end nonetheless. This one is definitely of the challenging type, but challenging questions because you learn a lot from them. All right, let me just bring this very quickly there. Oops, can we get the whole question to fit? It's very difficult to fit all of it. All right, okay, I've just about got it. Okay, here we go. And I'll just insert a page, blank page after current. Let's try see if we can blow this up. Can you see this okay?
Yeah.
Awesome. By the way, just so you know, this is really a stretch and challenge. This is one of the questions that was used for Cambridge University applicants, and it's a non-calculator question, so you can do it without a calculator.
Oh,
So
is it university questions?
It's not a university standard,
Oh.
It's year 11 standard. It's GCSE standard.
Oh.
So it's not, no, I wouldn't give you a university question. It'd be too scary to be doing a university question now. This is for applicants who are planning to apply to Cambridge.
Oh.
Yeah.
Is it for physics or in general?
For physics and engineering, and also wanting to do chemistry or biology. Sorry, natural sciences, sorry.
Oh.
Yeah.
Yeah, so do we use V equals frequency lambda?
Correct, very good starting point.
Do we have to find the circumference?
You don't need to find the circumference at all in this case. You won't need to find the circumference, but good that you're asking yourself those questions, but you won't need to find the circumference at all. So we know here, firstly, are you happy that this distance here is a wavelength?
Yeah.
Just like the other question where we had those crests, which were, sometimes you have crests that are circular or wavefronts that are circular. So you can either have them straight or circular. So you don't need to know the lengths of them. It's just the distance between them that's important.
All right, yeah.
So this is what you want to work out. You want to work out what this is.
Yeah. This is, yeah, so we need the frequency.
Yeah.
Which is 1 over time.
Good. And what's your time period?
It's a time plus 1 second.
Okay, so remember.
So is it 1.8?
Not quite. Not quite. So it says a stick at position X dips into the water. So it's dipping into water.
Yeah.
every 0.8 seconds. So what is this telling us? If it's dipping into water every 0.8 seconds, what is this value representing? Is it a time period? Is it a frequency? What is this?
Is it time?
Time period.
Yeah.
Correct. So this here is the time period.
Yes, is it 1 over 0.8?
Correct, absolutely. So the frequency is 1 over 0.8.
So it's 1.25?
1.25, which is the same as 5 over 4.
Yeah.
Good.
Then we need to
Excellent.
find out V.
We need to find out V, yes. So we've got F now. We now need to work out V.
F equals V over lambda. So is it 1.25 equals V over lambda?
1.25 equals V over lambda, correct?
Yep.
Yeah, that's absolutely spot on.
If we want to find V, can we use S equals VT?
Yes, S, that might be useful. And I like that you've thought about it. Very good,
Right.
excellent. S equals to VT, this might be a good savior.
Yeah.
We had
So
to
would
use
we
it for one of the questions, didn't we?
So, yeah. So S would be 2 centimeters,
2 centimeters, good.
which is 0.02 meters
0.02 meters
equals V times 0.8.
equals V times, you can't times it by 0.8 this time.
Yeah.
You can't times it. So you're saying here that the distance, 0.2, is given by, so you're saying that this distance is traveled in one time period. We don't know. We don't know if this distance is traveled in a time period. In other words, we don't know how long the wave takes to go from there to there. We don't know that time.
All right.
So we can't equate 0.02 to this in this equation because this time we don't know what that time is. So if we don't know what that time is, we can't work out what V is.
How about 3.5 centimeters?
And we still don't know how long it takes to go from there to there. We know the distance it travels, but we don't know how long it takes. If we knew how long it takes, then definitely the problem would be a much easier problem, much friendlier problem. But at the moment, it's not so friendly because we don't know that time. We don't know these times.
Yeah, so
but no harm. Sometimes there's absolutely no harm. Sometimes in just because you've got two things you don't know in your equation, don't be afraid to use it. So sometimes it's okay. And there's no harm in saying, okay, 0.02 meters is equal to V times T. But I don't know what this time is. That's okay. That's fine. Yeah?
Yeah.
So I'm just going to call this equation 1. So I have two unknowns. If you have two unknowns in an equation, if you want to find out what those unknowns are, how many equations do you need to form?
1.
Not quite. So
One extra one.
one extra one, correct, you're right.
Yeah.
So 3 unknowns, 3 equations, 4 unknowns, you've got the idea. Good. So I need to form another second equation. If I can form a second equation with V and T, then I might just be okay. So which can you think of a second equation I could form? So I've used this piece of information, I've formed this equation. Can I now use this to form a second equation?
B equals F lambda.
So you know, like how we formed this equation using this problem here, or what's presented. Can we form another type of equation using this diagram? What's given in this diagram?
0.035
0.035
equals VT.
So let's just think about that. I want to say if I write 0.035 equals VT. What's the problem with this equation?
We have two unknowns.
Not quite. This, to go from here to travel 2 centimeters, took some time. We don't know. We're just going to call it T1. To travel from here to there for 3.5 would not have taken the same time. So these 2 times are different.
Oh, right.
The time it takes to travel 3.5 is going to be different, surely, to the time it takes to travel 2 centimeters. So now we've got a problem. We've got 1, 2, 3 unknowns and only 2 equations. So there is a bit of a problem there. But there's something we could do. There's absolutely something we could do. Yeah?
Yeah.
Of course, that is why it is a Cambridge problem. There's extra tricks we need to think of here. And what we could do then is to say, right, this wave here, that's the crest at Q. It's now here. So it traveled all the way from this point where it dips to there in some time, which we don't know. And then we know that 1 second later, or in this time, it is now there. So how far is it from where it started off from, this wave crest Q? It is 3.5 plus lambda. It started off from here, it is now there. So the distance it's traveled is 3.5 plus lambda. So that is the S I'm going to use in this equation.
Yeah.
Now 3.5 plus lambda is equal to, V multiplied by, hang on, we know it's told us what the time is here.
Yeah.
T plus 1.
Yeah.
Following so far?
Yep.
So now this allows me to form, and I'm going to call this equation 2. So now using these 2 equations and using this equation here, do you reckon you can find a way to maneuver yourself and work out what the wavelength is? Just to make life easy for you, because I don't want you to fall into a trap, I'm just going to use centimeters. It's okay in this case, we can use centimeters. Generally, you did the right thing in that you're very vigilant. You always like to change things around to SI units, so that's very good. But in this particular instant, it's okay.
So is it like 3.5 plus lambda equals 2 centimeters?
Nearly there, but what are you going to have to do here, Anita? You're going to have to expand this bracket, aren't you?
Yeah. 3.5 plus lambda equals to VT plus V1S. VT plus V1.
And by the way, again, to avoid confusion, we don't need to call this T1 anymore because they've told us that this is time T and this is time T plus 1. So we can just use T here, VT, because that's the time T. And here we can use, that's why we've used T plus 1. Okay? Sorry, I should have made that clear.
Yep, so is it 3.5 plus lambda equals VT plus 1?
Not quite. Remember, you're expanding the bracket.
So VT plus V?
Correct.
Yeah. And 2cm equals VT. So is it 3.5 plus lambda equals 2 centimeters?
Plus V, yeah?
Yeah.
Yeah.
Oh, yeah.
Don't forget the plus V.
Oh. I'm a bit confused.
A bit confused?
Yeah.
Let's go through together, that's okay. So you got 3.5 plus lambda equals VT plus V, yeah?
Yeah.
But remember, equation 1 says that VT is the same as 2.
Yeah.
So in this equation where there's a VT, I'm now going to put a 2.
Yeah.
Are you following so far?
Yeah.
Good. But what do I know? I know from here, from this equation here, I know that lambda is equal to V over 1.25. Are you happy with that?
Yeah.
So do you reckon you can use this information now to get to the answer?
So 3.5 plus 1.25.
But it's not 3.5 plus 1.25 because now lambda here is this thing here.
Oh.
It's V
So
over 1.25.
So 3.5 plus V over 1.25
Correct. Which is equal to
equals
2
V
plus,
plus 2.
correct.
And 3.5 plus V over 1.25 minus 2 equals V.
Good.
And then 3.5 minus 2 equals V minus V over 1.25.
Okay. And what do you get as your V?
And as V 3.5 minus 2 is 1.5 equals V minus V over 1.25. So you do 1.5 times 1.25. Right. Oh, I'll do it again.
That's okay. Now, if I were you, what might even be easier?
All right. Would it be 0.6?
0.6 you get for the V.
Yeah.
Okay, and then what does that give you then for the wavelength?
Wavelength. So 0.6 equals 1.25 lambda.
Mhm.
And it will be 0.48.
But that's not there in any of these. Let's work through
So
it
would it,
together.
yeah, so would it be 0.6 equals 1.25 lambda?
Yeah, but I think you've just gone somewhere wrong, maybe where you've computed your V. Yeah. So if we just another way to think about this as well, sorry, Anita, I should have mentioned here. Of course, we replaced the lambda there. We could have also replaced the V because we know that V, and it would have been much easier, surely. I should have pointed that out.
Oh.
V is 1.25 multiplied by lambda, which is the same as 5/4 times lambda. So where there's a V here, I'm going to use 5/4 or 5 times lambda over 4. Yeah. So now we take all the like terms together. So we have 5 lambda or 5/4 of lambda minus lambda is equal to, so I've taken this lambda to the other side. And I'm going to take this 2 to the other side where it's become minus, just like this one became minus. So now I have 3.5 minus 2. Are you following so far?
Yeah.
Excellent. So now I have 1.5, which is the same as 3/2.
Yeah.
5/4 minus 5/4 lambda minus lambda is what? Lambda over 4?
Yeah.
Good.
Lambda over.
Yeah, because that's 1.25 minus 1 is 0.25 lambda, which is the same as 1/4 of lambda.
Yeah.
So what is your final value for lambda then? If lambda over 4 is equal to 3/2, what must lambda be?
3/2 times 4.
3/2 times 4, correct. The cross multiply. 12/2, which is 6. So the final answer is F.
All right.
Okay.
Yep.
So it's doable. It's quite demanding. Okay. And it's okay to do demanding questions because you learn a lot from them. You learn tricks. That's why it's always good to get yourself a bit out of the comfort zone. Good. So I'm really glad because what I wanted to make sure is that I wanted to assess how well you've understood what we were covering. And what I didn't want to do is gone way far and not actually assess to say, are you keeping abreast with all the finer nuances? And it was really good on the major part. You showed that you have a good understanding, but I'm hoping that you're learning a few tricks when it comes to calculations, because there were other areas where you're being caught out a little bit with either, especially on the echoes. Do you agree with that? Like dividing by 2. So with those ones, just take your time, really break down the problem. But again, once you got going and you understood what was going on, you were generally quite all right with that. What I say, I will send you, of course, this document in the video. Some of these questions are quite good, and it wouldn't hurt, especially the ones that you found tricky today, to try and revisit them, see if you can do them in, I don't know, a month's time, maybe 3 weeks' time, just to see, let me have a go at that. Can I do it, and what's my learning like? Do you have any questions for me then?
No.
Awesome, excellent. How did you find that session?
It's all right.
Good. Super. I shall then see you next week on Wednesday. Is that okay?
Next week. Yeah,
Okay.
that's okay.
All right, awesome. Have a
Thank
lovely
you.
evening, and I wish you a lovely rest of the week at school as well.
Thank you.
All right,
You
cheers now.
too.
Bye. That's
Cheers,
okay.
bye.
Thanks, Anita. Bye bye.
Thank you.
You're welcome.